Hello, good morning everyone. Today I would like to share with you the Fourier transform application. So this is the outline for the lecture 10, which is the response of LTI system, LCCDE, modulation, circuit analysis, and FFT. But this FFT is covered very little only. Okay, this is the Fourier transform pair tables. And this one also the same Fourier transform pair table in which you have the in time domain and in frequency domain. So let's say if you want to find this one in frequency domain, so you can check. Okay, exponent negative AT is what in frequency domain. Okay. Okay, this is the properties of the Fourier transform. This is also the same. And the response of an LTI system. Okay, I briefly explain on the response of the LTI system. Means that if you have complex signals, the response of a system can be determined by separately looking at each basic signal. That is so-called the eigenfunction of the LTI system. So the output signal of the Fourier coefficient, Fourier series coefficient is the input of the Fourier series coefficient that is scaled by the frequency response of the system. So we have the yt equal to the summation of the xn hn. Okay. In another way, the response for any input to the LTI system is simply the convolution. It's simply the convolution of the input and the impulse response. Okay. So what is convolution? Convolution is the multiplication in frequency. Okay, what's the multiplication in frequency? So for a non-periodic system, a Fourier transform of the output signal is the product of the Fourier transform of the input signal. So it means that the Fourier transform of the output signal is the y omega. Okay, y omega is referred to the Fourier transform of the input signal. This is referred to the x omega. And the frequency response of the system, this is referred to the h omega. So y omega equal to x omega multiplied with the h omega. Okay, so this h omega also is a Fourier transform of the impulse response, so it's a h. Okay, if you want to explain in terms of the block diagram, this is the block diagram. So the output signal is the y omega in frequency domain. So you can do it like y omega equal to x omega and h omega. And this h omega is actually referred to the impulse response. Okay. So for our LTI system, instead of doing the convolution means that this yt equal to xt convolute with the ht, or you're using the formula. This is the Fourier transform of the, by definition, the formula. So instead of doing convolution, the output of the system can be solved by first finding the response in frequency domain. Okay. The output of system can be solved by first finding the response in frequency domain. That is just what I told you. You can solve the response first. Okay, can be solved by first finding the response. So the response means that it's x omega. Like everything you transfer to the frequency domain. Then transform the frequency domain to time domain, which is the inverse Laplace transform. So after you get this in a frequency domain, the omega, then you can transform to a time domain by using inverse Fourier transform. So an LTI system that characterized by the linear constant coefficient differential equation, or we call it LCCDE, can be solved by the Fourier transform. So if we have the input and output fulfill, if you have input and output fulfill the LCCDE equation, we can obtain the system function, the h omega. by using the linearity and convolution properties of the Laplace of the Fourier transform. So this is the convolution property. Y omega is x omega multiplied with the hash omega. Okay, and if you want to find the hash omega is y over x. Now let's look at the LCCDE examples. Consider a stable LTI system that is characterized by the differential equation. So this is y prime plus 4 y double prime plus 4y prime plus 3y equal to x prime plus 2x. Okay, so using linearity and differential property. Okay, so this double prime y double prime you change to the j omega square y omega plus, so if you only have the y prime you change to j omega, so 4j omega y omega plus the 3yt, this yt change to y omega, so 3y omega equal to this one change to j omega x omega and plus with 2x omega. So you collect all the y omega here. You collect all the y omega, you factorize it, you just left the j omega squared plus 4 j omega plus 3 that is equivalent to the x omega j omega plus 2. So as I mentioned to you just now, hash omega is, okay, the hash omega is referred to the output over input, right? The y omega over x omega. So if you look at here, y omega over x omega, you get j omega plus 2 divided with j omega squared plus 4 j omega plus 3. So this one, how to solve it? We can solve this one, we can factorize it. Usually we assume that j omega is s. If you don't want to assume, also can. So you factorize it using the a and b and use the partial fraction expansion to find the a and b. Here I straightforward, I have found the a is equal to half or 0.5, b also 0.5. So I get the hash omega in frequency domain. Okay, it's like this. So if you want to get the hash t, the impulse response, so actually I can use the inverse Fourier transform to transform the hash omega into the hash t. So inverse Fourier transform. You can find using the Fourier transform pair table, and then you get back these signals. So it's 0.5 exponent negative t ut plus 0.5 exponent negative 3t ut unit step. Okay. Now let's look at another example. Find the system function and the impulse response for the yt that is called y prime plus 3yt plus equal to xt. So again, it's the same example like previous. So you change the y prime t to j omega y omega plus 3yt you change to 3y omega, xt change to x omega, and then you collect the y omega and x omega. You get the hash omega equal to y omega over x omega that is equivalent to 1 over j omega plus 3. Because you need to find the impulse response. That is how we solve the question. If you look at the question, is find the system function, and the system function is referred to the hash. Impulse response, this one is a hash omega and the hash t. One is in the frequency domain, another one is the time domain. Okay, you change using inverse Fourier transform, you get the hash t. Okay, another example is a modulating signal Vm equal to cos 2 pi 4000 t is amplitude modulating a carry Vc equal to 2 cos 2 pi 1500 kt. Determine the output frequency component. So here we have the Vc and we have the Vm. And we need to find the upper side frequency response and lower side frequency response. This is under modulation topics. Okay, never mind. Let's we go to the modulation topics first before I come to here. Okay, so what is modulation? What do you know about modulation? Modulation is the process of varying one or more periodic waveform. It's called the carry signal with the modulating signal that contain the information to be transmitted. Okay. So now we can see here modulation is also used to make the transmission of data signal more efficient by translating the data signal, okay, which occupy the low frequency spectrum into a signal occupying the high frequency spectrums. So normally it involves the multiplication of two signals. Which two signals? That is the modulating signal, or we call it as a data signal, and this signal is a low frequency. And the high frequency signal, or we also call the carry signal, and this carry signal is a high frequency. So modulating signal is used to vary the amplitude of the carry signal. Okay, this one we call as a amplitude modulation. So amplitude modulation, you have the carry and the data, carry signal and the data signal. So modulating signal or the data signal is used to vary the amplitude of the carry signal. Okay, so for example, if you have the Vm equal to rectangular t and Vc equal to the cos omega ct. So by multiplication, VAM, the amplitude modulation is Vm times the Vc. Okay. So from here we know that the Vm, the Fourier transform of the Vm is sin V omega m over 2. Okay. And then from the modulation property, okay, we have the cos omega naught t xt, you will get half of the x omega plus omega naught and x omega minus omega naught. So the Fourier transform of the Vm and Vc, multiplication of Vm and Vc, you will get this one. Okay, you will get this one. So when you combine, this is the xVm, right? So we combine both. So you have the half of the sine, because the Vm is sine. So sine omega m plus omega c over 2. So you see that is a combination of the Vm and Vc. If you have half, you have half here. And you have the sin, you also have the sin. And the signal is omega m over 2. Here also omega m over 2. Okay, here got omega m plus omega c. Here also omega m plus omega c. So it's a combination. Okay, it's a combination. So here have two set of the frequency. One is a carry frequency. Another one is the upper carry frequency and lower carry frequency. So upper is the omega m plus omega c over 2. Lower is omega m minus omega c over 2. Okay. So this frequency, this formula we can use to solve the example 3. So just now the upper side of frequency response is omega m plus omega c over 2. So omega m is referred to the here Vm. We have 2 pi 4000. And omega c we have 2 cos 1005k. Okay, divided by 2. That one is the upper side frequency response. And the lower side also the same, but just in terms of the minus. Okay, class? Do you have any question here? And then in terms of the circuit analysis, I briefly explain. So what you have to do for the circuit analysis is firstly you transform the function of the circuit element into the frequency domain. Okay, you change the function of the circuit element in the frequency domain. Then take the Fourier transform of the excitation. So if cannot solve using the Fourier transform, conventional circuit analysis technique could be applied to determine the Fourier, the frequency domain. Okay, but if you can, that means that you can continue. So then apply the inverse Fourier transform to obtain the response of the time domain. Okay, now let's look at the example here. Find the V out t in the circuit shown below for VIT equal to 2 exponent negative 3t ut. Okay, with the resistor is 2 ohm and the capacitor is 1 farad. Then this is the input is 2 exponent negative 3t. So as I told you just now for the circuit analysis, first of all is you need to transform. First of all is you need to transform into a frequency domain. Okay, what I mean here is, okay, let's look at here. If you have the R, you transform to a frequency domain, it's still R. And it's a capacitor, you transform a frequency domain, is 1 over j omega c. For the L, for the inductor, is j omega L. So this is what we call it a transform to a frequency domain. So now, the Fourier transform of the input signal, okay, we have the input signal is Vi, right? The input is a Vi equal to 2 over 3 plus j omega, which is, this is Vit, is 2 exponent negative 3t ut. If you use the Fourier transform, using the Fourier transform pair, so you can find 2 over 3 plus j omega. Okay? And next, you want to find the transfer function of the circuit, that is the hash omega. So hash omega is referred to the, okay, you want to find the hash omega, that is referred to 1 over j omega c, that is capacitor here over capacitor. So 1 over j omega c over the total resistor, yes. That is the 1 over j omega c for the capacitor and the resistor. Okay, so capacitor is 1, so you substitute the C is 1, resistor is 2. Okay, then you get like this. So you simplify, okay, you have the 1 over j omega divided with 2, this is 2 plus 2 j omega over 2. So you simplify like this. Okay. Since j omega usually we have only 1, so we divide by 2. Okay. Still remember previously you have learned before, if you have a S, we need a single S only, one S only. We don't want extra many S. So we only have S. So we divide with the number here 2. So we get j omega is single, is 1. Okay, so we get 0.5 over j omega plus 0.5. This is because when we use the inverse Fourier transform, it's easy. So the V out is the hash omega times with the V in. So hash omega is 0.5 divided by j omega plus 0.5. And V in we have is 2 over 3 plus j omega. Okay, again we use the partial fraction expansion to solve. So I find the A is 0.4 and B is negative 0.4, and I substitute in the value of A and B. I get V out like this. Okay, 0.4 divided by j omega plus 0.5 minus 0.4 divided by j omega plus 3. So taking the inverse of the V out, okay, so this is just a constant. Okay, so 1 over j omega plus 0.5, I will get exponent negative 0.5t. Here also the same. Okay, I get exponent negative 3t ut. Okay, class, so that's all how I solve using for application, the circuit analysis. Here I share with you another example of the circuit analysis. So find the output voltage for the circuit given below. You have the V in here and the V out here. V out is voltage across the inductor, and you have the resistor R. So the circuit can be described by the differential equation. So V in VIT equal to R IT plus with the L DIT over DT. So this is for the V in. And the V out is, this one is L dit over dt. So taking into the Fourier transform, VIT change to VI omega, RIT change to RI omega. That is in the frequency domain. and L dit over dt. So this one is a differential. So I prime you get j omega, right? So j omega L I omega. So you take out the I omega, you have left the R and the j omega L. So I omega actually is referred to the VI omega divided by R plus j omega L. So V out omega from you taking the Fourier transform of V out t, you get j omega L I omega. So the response, the system response is the V out over V in. So V out is what? Okay, V out is j omega L I omega, and V in is I omega V in. Okay, V in is I omega R plus j omega L. So you cancel out this one, you get j omega L over R plus j omega L. Okay, class, there's a exercise for you, which is in the lecture slide, lecture 10 slide. You have the one exercise here, so you can try it at home. And the final answer is provided. Last but not least of this topic is the power analysis. There is the Parseval theorems. So what you need to know about the Parseval theorems is this one, the power associated with the signal omega, the W. So the watt, okay, the energy carried by the signal and the W. So for the W1 ohm, you have this kind of formula. Okay, so the Parseval theorem states that this same energy can be calculated in the frequency domain as this one. So you need to know this kind of this formula. Okay, integration from minus infinity to infinity, x squared t dt, or 1 over 2 pi integrate x modulus of the x omega squared. So one is in the time domain, another one is the frequency domain. So you can choose which one to use. Okay, the next the example is like this. The voltage across the 10 ohm resistor is Vt equal to 5. Exponent negative 3t ut watt, and find the total energy dissipated in the resistor. So just now I already told you how to get energy, how to find the energy, either you're using time domain or in the frequency domain, right? So I show you now in the frequency domain how to get in the how to get in time domain first. Okay, still remember the formula? I show you again. Okay, so this is the formula. Okay, this is the formula. Okay, so energy is equal to the integration minus infinity to infinity xt squared dt, or xt xt conjugate t dt. Okay, so xt is what? In this case, the xt is referred to the 5 exponent negative 3t ut. Okay, what is the function of the ut here? If you look at the ut, actually is the limit is from 0 to infinity. That's why, so you change the limits to 0 to infinity. And the voltage across a 10 ohm resistor, so you have the constant with 10. Okay? And then you have the xt. So this xt is referred to this one, 5 exponent negative 3t. And then you square. Okay, you square the 5 exponent negative 3t, you get 25 exponent negative 6t. Okay, you multiply 10 with 25, you get 250. Okay, and then you integrate the exponent part, you get exponent negative 60 over negative 6. You substitute the value, you get the 41.671 joule. Okay, this is you solve in time domain. If you want to solve it in frequency domain, also can. But you have to convert everything into a frequency domains. For example, you have the Vt. So you need to change to the V omega. Okay, 5 exponent negative 3t ut, you change it into 5 over 3 plus j omega. Okay, the formula is like this, 1 over 2 pi x omega squared. Or you can x conjugate omega and x omega. So for the energy displayed for the 10 ohm resistor is 10 over pi. Okay, and then you have this one, the x omega. This is conjugate one. This initially is 5 over 3 plus j omega. You conjugate, you get 3 minus j omega. Another one is the x omega. Okay, and then you multiply in, you get 25, 9 minus omega square. Okay, the limit is from 0 to infinity again. Okay, from here, how to get here? We have through a formula. That is the integration of u prime x divided by 1 plus u prime square and ux square equivalent to inverse tangent ux. Okay, so if you look at here, I have this one. Okay, I take out the 25, I just left 1 over 9 plus omega squared d omega. So I factorize it, I take out the 9, so I left 1 plus omega over 3 square. And from here, you know that the ux is what? This is the ux, right? So ux is referred to omega over 3. If ux prime, that's equal to 1 over 3. Okay, if I if I put into the value, so I will have this one is 1 over 3 divided by 1 plus omega over 3 square, d square. But this one, initially, I only have 1, right? This is the original signal, the original value. But what after you substitute, you get 1 over 3. So you need to times with 3 to cancel the 1 over 3. Okay, this one because you want to remain the same value. And then at the end, you cancel out, you will get 1 over 3 inverse tangent omega over 3. Then you substitute the value 0 and infinity. Okay, substitute the value 0 and infinity, and you get the answer. The answer is the same. The answer is the same. 250 divided by 6 is equivalent to 41.67 joule. So that's all for the lecture 10 Fourier transform application. I hope you can understand and enjoy your watching. Thank you very much, class. Bye.